So our next legend, first legend of the afternoon, our last afternoon, is Walter Giger. Walter's from AVOG, the Swiss Federal Institute of Aquatic Science and Technology, which of course many of you probably know is legendary in and of itself. AVOG is a legend institution for setting the bar for international excellence in environmental research. Walter's highly recognized for developing analytical methods for organic environmental pollutants, also for identifying new emerging contaminants. I hope you'll talk some about that today, and conducting studies to understand their fate in the environment. Walter also served as associate editor of the premier journal, environmental journal ES&T, for many years. He served on several international committees, including the National Academy of Sciences Committee on Drinking Water Contaminants. And Walter's also been recognized by ISI as one of the most cited authors in the field of environmental organic chemistry. So please join me in welcoming Walter Giger.
Well, thank you very much, Susan, for this introduction. And also, thank you very much, Susan and Vic, for inviting me. I'm kind of very proud to be among this group of legends in environmental chemistry. I know that I'm the first speaker of this afternoon session, and you all come back from lunch. So I will do my best to keep you awake during the next 50 minutes. As you can see in my title, which is a kind of a double title, the first part is referring to a relatively famous song, and the second part is taken out of Greek mythology and Shakespearean theater. I will use both of them, and particularly I will try in the end of my talk to evaluate a bit of these environmental chemists, particularly analytical environmental chemists. Are they now more Heracles or more Sisyphus? Now, I thought I would have to introduce myself a bit, like almost everybody did, and going rapidly through my CV. I will do that using this table here, which I put together about a year ago, and it goes back on some remarks which I heard from Werner Stumm years ago. And it shows in 3 columns: position, research, and conferences. And then it shows in the rows, it shows the various stages of each particular career steps, which probably most of the researchers go through. I started as a graduate student at ETH in Professor Willy Simon's group, actually together with René Schwarzenbach. We were in the same group. We founded a handball team, which was called Simonia at that time. There was one difference between René and me. He worked on, he already told you, on this computerized mass spectrometry. I worked in NMR, on nitrogen-14 NMR. And the difference between him and one of the differences is that in my examination committee was Professor Richard Ernst, and he won the Nobel Prize a few years later for his NMR work, but unfortunately not directly related to my thesis. Then I went on. Right after finishing my studies, I went to AVOG, where I started as a junior scientist. I was postdoc, also in Woods Hole, in the group of Max Blumer. And then I later on became a senior scientist, a group leader, and so on. And you can see here what we usually do as a researcher. We are primary producers in the first 2 rows, and then we get the secondary producers or consumers or herbivores in the 3rd row. In conferences, we first go through posters and oral presentations, and then we sometimes get into scientific committees, and then we make it up the ladder or down in the table here. As department heads, we get tertiary producers, or as Werner Stumm put it, carnivores. We get invited to plenary or keynote lectures, and then comes the last row, which is still open here. You retire, you become a retiree, or a nicer word, emeritus. They ask you to work as a consultant or as a historic reviewer. And they still ask you to give plenary lectures in some conferences, but sometimes you have to deliver, or you ask to deliver dinner or lunch talks. And this legend lecture today, I consider to be kind of in between a plenary talk and a lunch talk. Now, I'm aware that 50 minutes are a long time, so I don't want to bother you with a frontal lecture for 50 minutes. I try to do something which I would call scientainment, combination between science and entertainment, like infotainment, information entertainment. I first thought that I had invented a new word when I created this, but then using Google, I found about 1,200 entries for this term here. I'm going to base my scientainment on two pillars. One is I will play you some music, and I will ask you, I will play you some songs, folk and country and blues music, and I will ask you whether you know the singer who plays it. Then I will also ask you some other questions which are related to history of chemistry. I'm aware that this symposium is co-sponsored by the environmental people and by the Division of History of Chemistry. This puts us back in some earlier century to some time. The songs, by the way, they are connected in a way to my activity because I like to listen to this kind of music during the many hours which I had to spend to write all these manuscripts. Firstly, and then later on to evaluate all these manuscripts which I had to work on. So this music kept me in good mood during all these long hours which I had to work. Now I will organize my talk. Well, this is the first song here. It's the title song of my talk. And if you know who is singing, just shout it out. This is so easy, the question. It's almost a rhetoric question. So here I must also say that I borrowed this idea of taking this song as kind of a background of my talk. I borrowed it from a real legend in another field, a legend in mountaineering and mountain climbing. His name is Reinhold Messner. He used that song in the early 80s. I heard a talk, a slideshow given by him on his adventurous climbs on Mount Everest, first without oxygen, first solo, and he used this particular song as a background for his beautiful slides. So I borrowed this idea basically from him. Now, this is the table of contents of my talk. I will first talk a bit about what are legends. We already had heard this detailed definition this morning. I will give you a bit another view. And then I mainly focus on organic pollutants. I will go through some key players, mentors for me, some landmarks, milestones, events. I will discuss pollutant types and not so much analytical methods because I think we have already heard many details on them in earlier talks. And I hope I don't run out of time to present to you some recent case studies on non-phenolic compounds, some other phenolic endocrine disruptors, on benzotriazole and perfluorochemicals. So what are legends? If you look it up in Wikipedia, they actually tell you that legends are either events or happenings or persons or animals of which it is not really proven that they ever existed. So I give you one example. This one here, this is connected to my title. It's the death of Hamlet, which is not really true. That it's not proven that he ever existed. He was just taken in Shakespeare's drama. Now the next question is, what are the Swiss legends? This is not an official question. I just show you two of them. This is one here. This is the so-called Rütli-Schwur. That's the foundation of Switzerland in 1291. Here the people started Switzerland. But modern historians, and this is in all school books in Switzerland, but the modern historians tell you that most probably The only thing happened at the 1st of August 1291 on this Rütli meadow was that some cows were grazing and producing milk and manure and greenhouse gases. Now, if you go to the persons, these are the two Swiss legends, the real legends, not the environmental chemistry legends. It's William Tell and Walter Tell. And you know, William Tell, he was kind of a rebel. He didn't greet the hat of the governor, and he had to shoot the apple from his son's head. And then later on, he also shot the governor. I think nowadays he would probably be called a terrorist. In the Greek mythology, I have borrowed these two figures here, Heracles and Sisyphus. And you know, Heracles, he was a real tough guy, and he solved all the problems. He had about 10 jobs to do, and did all of them, basically. On the other hand, Sisyphus, he had only one job, to carry up this damn stone, and the stone fell down all the time, so he had to start from scratch again. So the question which I would like to discuss in the end is, I said it already, are we now more Heracles or Sisyphus? Both have nothing to do with environmental chemistry, but Heracles was actually the first sanitary engineer. You know, in one job he had to clean the stable, the Augeas stable, and he deviated the creek and cleaned the stable just by running the creek through the stable. So he was, I guess he must be the first sanitary engineer, although it's not really a good thing. Nowadays he probably would not get good notes for that because he contaminated that creek. All right, so let's get a bit more serious history of environmental chemistry. When was the first report on organic pollutants? I give you 1775 or 1976. Well, you can answer the question yourself and note down whether you are correct or not in the end. It was 1775. It was this person here. Does anybody know who that is? His name is he wrote a book in 1775, Surgical Observations, which means in this book he described the higher incidence of skin cancer among the chimney sweeps of London. His name is Sir Percival Pott, and it was about 150 years later when the scientists were able to identify benzoapyrin as a carcinogenic active factor in soot. Now comes the second song. This one is connected to this person here.
Well, I was born a coal miner's daughter.
Does anybody know who sings?
In a cabin on a hill in Butcher Hollow.
Yeah, Loretta Lynn.
We were poor, but we had love. That's the one thing that Daddy made sure.
Now, this was my first mentor in the environmental chemistry. You have already heard about him by René Schwarzenbach, Max Blumer, who worked at the Woods Hole Oceanographic Institution. He taught me, introduced me into PAHs, into the world of hydrocarbons, of polycyclic aromatic hydrocarbons. He had been, for many years, working for Shell Company in Houston in the petroleum field, and then he moved to Woods Hole and was there working kind of on the other side. He still worked on hydrocarbons, but he was looking at the biogenic hydrocarbons in algae, and also he dealt with this West Falmouth oil spill, which had happened just a few years ago. I was there in '73. And you see here still an old mass spectrometer. We have heard about these machines where you had to push a button and then you had to use this special ruler to to get the mass spectra of the photographic tape. He was a real Swiss watchmaker type, very pinpointing, and he didn't really allow many other people to work on his instruments. And he also showed me that, or I learned from him, that it's a good idea to work at interfaces, to work at partly in the geochemical world and partly in the environmental world, because then you can kind of interact or combine the two fields. The second person is shown here. Does anybody know him? Yeah, René is excluded. This is Kurt Grob, the person who was a real pioneer in glass capillary gas chromatography. I have a special relation to him because he was already my chemistry teacher at high school and lower college. At that time, he was analyzing cigarette smoke, and later on he switched to environmental samples, to atmospheric contamination, and to water samples. And then many years later, he actually joined EAWAG, and he became a co-worker at EAWAG. These two chromatograms you have already seen in Larry Keith's talk. They show in the upper trace the analysis made by packed column of 3 meter length, and on the lower part the same sample analyzed by a 30 meter long glass capillary column, showing the difference of separation efficiency. These two chromatograms were actually on the cupboard in Kurt Grob's laboratory, and every time he had visitors, he showed them these two chromatograms, and then he opened this cupboard, which contained about 200 or 300 glass capillary columns, which were worth lots of francs at that time. The capillary columns were actually much later introduced here in the United States, in Europe, particularly based on Grob's glass capillary columns. We used them already right from the beginning. In our group, we have actually never really used packed columns. We just started with capillary columns, and we profited very much from Kurt Grob and his wife, who were just next door, and we always could check out their newest developments. He also had developed what is called closed-loop gas stripping procedure for measuring volatile hydrocarbons and so on. This was, I think, the first time it was possible to analyze in the nanogram per liter range for organic contaminants. Now, my third mentor has been shown several times already during the last 2 days, Werner Stumm. He was director when I started at EAWAG. He had a vision. He wanted to change EAWAG, which at that time was a bit sleepy consulting engineer institute. He wanted to change that institute and to get it to become the Harvard of aquatic science and technology. To achieve this goal, he hired what I call here a group of young and wild scientists and engineers. And I don't read you the names here, but there are also some Americans among them. There is Mike Kavanagh and Paul Roberts, and René Schwarzenbach is in that group too. I have put him in bold letters here because I actually hired him and not Stumm. So what I learned from Werner Stumm was his generosity, which really, we heard about that already by other speakers here, but also I learned that you have to, best thing to guide a group of scientists is to set them relatively high goals, relatively high objectives, but also reachable goals, and then to give them as much freedom as possible so that they have to struggle themselves and they can fulfill the goals themselves. All right, so this is a quote here, actually 2 quotations. To measure is to know. If I cannot measure it, I cannot improve it. This is the slogan which I followed actually through almost all my career. And does anybody know who set these quotations? I give you choices here. Isaac Newton, William Thomson, Marie Curie or Albert Einstein? You can make up your mind. I help you a bit by giving the picture of this person. So it can't be Marie Curie, looks different. It can't be Albert Einstein either. So it must be one of these two guys. Actually, it's William Thomson. Nobody knows him. He has another name. He got into British aristocracy, and he was called Lord Kelvin. So this physicist, I think he's of Irish origin, but was a professor in Scotland. He created these two quotations. And now comes a song which is not directly connected.
Busted flat in Baton Rouge, waiting for a train, and I was feeling near as faded as...
Great, it's Janis Joplin. I'll just let it go. It's not so loud because she will get much louder afterwards.
They rode us all the way to New Orleans.
So it's me and Bobby McKee from... You can hear it now, eh?
I was playing soft while Bobby sang the blues. Windshield wipers slapping time, I was holding Bobby's hand in mine. We sang every song that Javi knew. Freedom is just another word for nothing left to lose. Nothing.
Next question. History of environmental sciences. You know her, I guess, many people. Yes, it's Rachel Carson. In '62, she wrote this book. We already have heard about that too, Silent Spring. That was had quite a big impact on me. I read it when I was a postdoc in Woods Hole, and I also read it again 40 years later, and I must say that she really put things into perspective, and many, I think, environmental scientists try to follow up what she has actually put up. Here I have a song which is connected to her, or partly connected.
How many roads must a man walk down before you call him a man?
Told by his,
How many seas must the
which is somehow related. I think they have some relations as being protest people here in the United States.
How many times must the cannonballs fly?
So now let's get a bit more serious. All these organic chemicals which have been studied and which will be studied in the future, I try to organize them in what I call the polarity volatility diagram, with one axis the polarity here on the vertical side, and the horizontal axis the volatility. You can group the chemicals roughly or coarsely in volatiles, semi-volatiles, polar hydrophilic, amphiphilic, and non-polar lipophilic chemicals. And if you go through the earlier first part of environmental chemistry, you see that most of them, most of the chemicals, the pollutants studied, are kind of in this lower part here, and also going to the left here. This is actually connected to the problem that gas chromatography, I come back to that, is dealing with that. And for these chemicals up here, you need either liquid chromatography or you have to derivatize your chemicals. Now comes the next question. History of chemistry. Does anybody already recognize this person? Sweet, huh? Yeah, he invented chromatography. Here is his first chromatograph, published in the Berichte der Botanischen Deutschen Gesellschaft. Now the question is not his name. The question is, was he Italian, Russian, Polish, or Swiss? Was Russian, okay. That's always an easy question. And this is what he published in 1906. this technique to separate pigments from green leaves, and he called it, this technique, chromatography, meaning writing in color. I think the environmental analytical chemists and many other analytical chemists would have trouble if they would not have this method. In both modifications, in the gas chromatography part and in the liquid chromatography part.
Take the ribbon from your hair, shake it loose and let it fall, laying soft upon my skin, like the shadows on the wall.
Who is from California?
Come and lay down by my side.
Huh? It's
till the early morning.
Chris Christopherson. Famous, he also wrote lots of songs. I think Me and Bobby McGee, which was interpreted by Janis Joplin, was also from him.
Make it through tonight. I don't care who's right or wrong.
Doesn't want to show here. I already referred to that already. This shows this volatility diagram, and it shows the application ranges for gas chromatography, the lower left part, and the upper part for liquid chromatography. There's a typo here. And there's also an overlapping part here. I would predict that in the future only a small part of analysis will be done by GC or GCMS. Most of it in the future will be done by LCMS. I will come back to that prediction later on in the talk. Now let's put in some classic contaminants in this diagram. The ones which I worked and my group worked with: petroleum, hydrocarbons, PAHs, then the classic DDT, biopersistent, polychlorinated insecticides, PCB, dioxins. They are somewhere in that range. And on the lower end, on the left corner, we have trihalomethane and perchloroethylene, the volatiles, which we worked upon some years ago. And then there are the gases, the atmospheric problematic compounds here, the PN, freons, and methane. So these are all covered by gas chromatography. Atrazine as representing other herbicides and pesticides. And if you go further up to the right corner, you'll come to NTA and EDTA, two complexing agents, which have been or still are widely used. NTA is also used as a phosphate replacement in detergents. Here you need to, if you still want to use gas chromatography, you have to derivatize them. And then up in the right corner are the surfactants. So I would call these the classic contaminants. And in our group, we have mainly focused on this upper corner here, because, well, after having been down here and here, we moved up to that corner first by using gas chromatography and then later on by using liquid chromatography, first with fluorescence, UV absorption and fluorescence detector, and then later on with mass spectrometry. So this group of chemics I will call the classic pollutants. Now comes the next question. When was the first observation of effects caused by polar organic water pollutants? Was it in Greek mythology? Remember Heracles and the Augeas table? Was it in the late 50s, early 60s, or was it 1986? Huh? Late 50s, that's correct. And what was it? Right. Was this here, this formation of foam caused by branched ABS, branched alkyl benzene sulfonates, these anionic surfactants, which did not degrade in wastewater treatment and in the rivers, and which caused these foams in the treatment plants, but also in the surface waters. This problem was solved by introducing LAS, the linear alkyl benzene sulfonates, and these foams disappeared. And for many years, the LAS was considered to be a very good chemical because it's degrading and it removes this foam problem. In our studies in the 80s, checking out what compounds are left in digested sewage sludges, we found that LAS is probably a major, if not the major constituent of digested sewage sludges. It shows up in about 5 grams per kilogram dry sewage sludge because it's not anaerobically not degraded at all. And this has been not, well, it was a long evaluation of what it means. In Switzerland, digested sewage sludge is not a problem anymore because it's not used on agricultural land anymore. It's incinerated. But in other countries, the material is still used as a fertilizer on agricultural lands. Now this one here goes a bit long until the singer starts. It almost sounds a bit Scottish, but I think it's an American singer. Rod Stewart, yeah. Rhythm of my heart. I must also say that I used, for getting these songs, I used iTunes and iTunes Shop, and all is legal. I bought all the songs. So no illegal copying. And I could also remark that it's relatively easy, once you have this iTunes Store under control, it's relatively easy to insert them into PowerPoint. That's what I did here. It gets a bit more complicated when you want to kind of cut out pieces, then it just takes longer and you have to spend more time. But I can just recommend it, it's relatively easy to do. Now comes another event which was happening in Europe. Does anybody already recognize it? Schweizer Halle, yeah. This fire, well, I might just explain it. This fire, which caught, this was a storehouse which caught fire at night of the Halloween night, actually, 31st of October. And in the morning, the whole hall was destroyed, and through the outlet, which normally takes cooling water untreated into the River Rhine, there was this red colored water coming out, which the company said this red color is a harmless compound. This is actually true. It's a fluorescing chemical, but this chemical was used to mark very toxic chemicals, and it led to the Schweizer Halle in 1986. It led to these problems here, and it was actually, this was also on the cover of ES&T in 1988, and it created these cartoons in some German newspaper. Here I think it comes a song. There's also coming up.
Came out west together with a common desire. The evil we had might have set the West Coast on fire.
Huh?
2 months later, got
No.
trouble in mind.
No,
Oh, my baby moved, I lived
Amy Harris, yeah.
But it's alright, 'cause it's midnight and I got 2 more bottles of wine.
So here's the sound of fire. What was stored in the storehouse here, all these chemicals in these tons here, and this what the tons, the mass flow which was found in the River Rhine just below Basel. You can tell that most of the chemicals found or stored here in larger amounts were found in the river, but there were also some which were not stored to larger amounts. Atrazine was not stored at all, and oxydicyl was only a small part. So it later turned out that this was a continuous chronic contamination from another place in the company. And this one here, atrazine, was caused by a competing or another firm which had an accident with atrazine, and which just happened at the same time to discharge this wastewater with atrazine into the treatment plant. The sound wave, as it was called, could then be followed down the River Rhine. Here are measurements at Bad Honnef, that's at kilometer 640. Here are the chemical measurements, this fluorescence peak, and the sum of the thiophosphoric acid esters. And on the lower part, you see biological effect measures, Daphnia and esterase activity. And I would pretend this is one of the few cases where it really was possible to measure at the same time the chemistry, the chemicals, and the biological effect. This is something which not happens too often. All right, so the sound wave was also published in ES&T in 1988. This is taken out of this paper, and this just shows the mass in tons which were discharged into the river and which then flow down the river from Basel here down to the North Sea. The whole thing was also modeled afterwards, so we were able, using chemodynamic modeling, to predict the past, to model this event here. The Schweizer Halle had a big impact on the environmental science scene in Switzerland, because all of a sudden many politicians thought that, or changed their opinion that environmental science is something which has to be supported, and these politicians were not only in the normal politicians, it was also in university politics quite a change. So here are some comments on the analytical methods. What we normally need is a sampling, enrichment, separation, detection chain. That's the normal procedure. And I just listed some of the most important techniques which are used. Some of them are relatively new. And I would repeat that I would predict that in the future, this here, large volume injection, combined with LC tandem MS will probably be the key instrument for environmental analysis, because that you can get rid of all the sample treatment, you can analyze a tablespoon or teaspoon and get the analysis done. This is already pushed by people who are studying pesticides in drinking water and mineral water, and it's pushed, for instance, by Jennifer Field in Oregon, who analyzes illicit drugs in wastewater with this technique. There are also modern developments, GC-TOF-MS. I show you a short example. And there's increasingly applications of high-resolution techniques. This could be a lecture on its own, what's all is going on the mass spectrometry side. What is very important is sensitivity and selectivity and Last but not least, validation and quality control. I think these things have to be developed right from the beginning, and we have seen that there's increasingly pressure to do this validation right from the beginning and not just afterwards. All right, I don't want to go into more on the analytical side. Now, the emerging contaminants, that's a term which has been created. I don't really know really by whom it was created. Everybody uses it. It's, again, a term which cannot be translated into German, so we even use it in German language. And some of them, the polychlorinated paraffins, the polybrominated flame retardants, and the organophosphoric flame retardants, emerging contaminants, which can be handled by GC methods. But most of the emerging contaminants up here in the right corner, drugs, antibiotics, hormones, diagnostics, they are analyzed by LC-MS. If you want to get the definition on what is emerging, I recommend you to read the lead article in this special issue of ES&T of December 2006, in which the guest editors tried to define what they really understand under emerging. From my point of view, among the emerging contaminants, it's particularly the polar persistent organic pollutants. Sometimes I already call them polar pops, which the real pop people don't like too much. But I think there are some chemicals up in that area which will be a topic of studies in the future and already now are causing problems. There is the fluorinated compounds, still is this alkyl phenol ethoxylate, and there are the benzotriazoles. These yellow ones are actually the ones which I will give you some explanation in the next part of my talk. Now, these non-phenolic compounds, I just summarized a bit here what we know about them. We know that they are derived from alkyl phenol polyethoxylate surfactants. They degrade partly in the treatment. More lipophilic metabolites are created. And nonylphenol itself is a dead-end metabolite under anaerobic conditions. It's also an endocrine disruptor. But the key compound is this hydrophilic NPECs, the carboxylated products, and they even show up at the highest concentrations in treated wastewaters. This is a historic chromatogram, 1980. I think this is one of the first chromatograms in which we found these nonylphenols, the nonylphenol 1 and 2 ethoxylate. This work was done by Euripides Stefanou, and we just were looking for phenols, and then we always saw these clusters of peaks. And thanks to the GCMS, we were able to identify them in 1980 as the nonylphenols. We then went on and we found them in high concentrations in sewage sludge, and here we managed, I think the only time we managed it, to publish a paper in Science. It was also rejected the first time we sent it in. The reason for rejecting was that this is probably a European problem. We didn't give up, and it was finally published because we already had samples from our friends in California which showed that it was also an American problem. This shows the key person in this alkyl phenol stories. This is Maria Nahel, and this is Christian Schaffner, and this must have been at the times where I still was smoking the pipe. Must have been around 85 or so. All right, so it's relatively well known what happens to these nonylphenols. It's degraded on the polyethoxy side, and here is this NP1 EC, which is kind of a key metabolite on which we focused in one of our last theses which we were doing. Felix Wettstein studied this 1-ethoxylate, carboxylate, in a mass flow study through a treatment plant. You see there's an activated sludge treatment here. In this case, it's actually produced. There is more coming out of the aerated sludge treatment. and it's removed in the sand film. The branched ones which degraded faster, and the reason for that is that it follows a completely different mechanism than the normal N-alkane degradation. So we could show that it's a split off of the alkyl group here at the quaternary or close to the benzene ring, and this is not the same as when you degrade, for instance, LAS, where it starts at the end of the N-alkane chain. All right, so we could also combine this study with colleagues who work on the effect side, with John Sumter and Ed Routledge at Brunel University, and they used a yes test to check on the estrogenic activity of these individual isomers, and there's quite a big, a factor of 100 between the different isomers difference. So this leads to the proposal that the risk assessment of nonylphenol should actually be done by doing individual differential degradation and checking on different effects of the nonylphenol isomers. And there might be a need for some similar system for toxicity equivalents like we have available or was developed for PCBs and dioxins. All right, so how much time do you have left? 1 minute. All right, let's just go through this part here. Now I have to show you this one here. This is a picture which I borrowed or I received from Jerry Snore, and it shows the European cow, and it also shows you where Switzerland is, and it helps you should remind you that Switzerland is not Sweden. Sweden is up here. All right, so let's just come to the last part. Let me just put that off here. So are we now more Heracles or Sisyphus? That's kind of the key question. I would say it's mixed. I think in some parts, the environmental analytical chemistry has proven that it can solve problems. It can at least help to solve problems. It gives identifications and quantitations of inputs. And so if you want to take measures against that pollution, you are in a much better position than if you would have just collective parameters. On the other side, if you look at all these emerging contaminants, you can just wait for the next one to come. So what's next? And I would just put up here a few of chemicals which I would expect that they will come in over the next years. More of these polar pops, additives, biocidal products, new pops, normal pops, and the substituting chemicals might also be a problem. I would like to show you 3 potential candidate polar pops. This one here, does somebody knows it? Sucralose, yeah. This package, or in my Starbucks coffee. This is a sweetener which is almost not degradable. It's used all over the place. It has no real toxicity. It's accepted as in food products, but it shows up in waters, in wastewaters, in surface waters, and it can be predicted that this chemical will also be in the drinking water because it's persistent and polar, and it goes through the barriers of drinking water treatment. This one you probably don't know. This is called torcetrapib. It's a pharmaceutical which was developed by Pfizer company and was announced as a coming blockbuster product for increasing the high-density lipids. And you can look at it and tell that this will cause environmental problems with these 9 fluorine atoms. There were discussions in the company, but it was then stopped, but not because of the environmental problem, because of problems they had in phase 3 testing with heart attacks of patients. This one here is very sure a common candidate, the polar pops, a fullerene. Not the fullerene itself, that's not water soluble, but once you functionalize the fullerene, and people are doing that already, you get what I would call nanopolars. Not new, but still unsolved. Earlier on, this was called humic acid or Gelbstoff. Now it's called natural organic matter. Now I'd like to acknowledge these people here. I just put down the names of those people who were involved in the studies of which I showed results. I've had many more co-workers, and if you are interested in to read on them, there is a brochure, the Giger Group 172 to 207, which you can download from the internet on this address here. I have some copies here, so if somebody is interested in the hard copy, there's also a CD with most of the publications. So now I think this is the end. I would like to thank you for listening and answering the questions.